We'll see the difficulties quantitatively later. I think I just mentioned about it in the previous session also. But then we are now going to look at the concept, not the concept, the proven theory of Mach number independence in hypersonic flow. Mach number independence in this context means many of the aerodynamic coefficients, like when they are expressed as non-dimensional parameters, they can be shown to be practically independent of Mach number in hypersonic flows, which means that once you have some value for those coefficients, which you have got at say lower hypersonic velocities, you can approximate them to hold for even higher values of Mach numbers, because the expressions by themselves are Mach number independent. So that's what we mean by Mach number independence. We'll look at it or how we arrive at this conclusion. For the first time in this course, now we are looking at the governing equations. Governing equations for steady inviscid flow. Given that the energy and the momentum equation, I have just written it for the x direction. So you have two other components for y and similar components for y and z directions, because momentum is a vector. So what I have written here are the continuity equation, x momentum equation, and the energy equation respectively for steady inviscid flow. Steady because we are not considering the dou by dou t term. Inviscid because we are not considering the pressure force in the momentum equation, as well as in energy equation also we are not considering dissipation due to viscosity. So for steady inviscid flow, we can write the governing equations in the partial differential form. This you would have seen several times earlier, starting from fluid dynamics to some extent thermodynamics, etc. So we are just looking at them. Now, the statements are fairly obvious. The first one, partial d by dx of rho u plus partial d by dy of rho v plus partial d by dz of rho w is equal to 0, which is basically the statement of conservation of mass, and we call it as a continuity equation. And what we get as rho I equals constant, etc., are from based on this expression. Similarly, the momentum equation just equates, based on the Newton's second law, equates the rate of change of momentum to the forces. Now, what is the momentum terms? Rho u dou u by dou x. Sorry. Rho u dou u by dou x. So you have rho u, that is the mass term multiplied by the velocity. So rho u dou u by dou x plus all are in the gradients in the respective directions as we derive the differential equations. The conservation equations in the differential form. So rho u dou u by dou x plus rho v dou u by dou y, etc., is equal to minus dou p by dou x. The P there indicates static pressure, or in general, the term comes from the consideration of the pressure forces. So the lone term that we have on the right hand side is coming from the forces, which is only pressure force, because we are not considering other forms of forces. We are not considering viscosity, viscous forces, because it's inviscid flow. We are not considering forces like gravity, gravitational force, or the body force, etc. So the only force that we are considering is pressure. So this is so that's X momentum equation. We have similar equation for the other two directions. And the third one is the way energy equation written in terms of entropy gradients. U dou s by dou x plus v dou s by dou y plus w dou s by dou z is equal to 0 comes straightly from the conservation of energy. So these three equations are the governing equations for steady inviscid flow. Keep in mind, I didn't say supersonic, hypersonic, etc. So the Mach number, etc., is not a parameter. We have not considered anything for this, for looking at this equation. So this is applicable for any range of flow velocities, as long as the flow can be assumed to be steady and inviscid. Now, we are trying to, what we are going to do is to non-dimensionalize this equation. You would have seen this earlier also in other topics, non-dimensionalization of governing equations. What is a big advantage of it? When you non-dimensionalize an equation, when you properly normalize it, we can reduce the number of variables that we need to consider at any given point of time. So that's one major advantage of having non-dimensionalization. I often quote this example of flow past cylinders. Probably I've mentioned it earlier also to you when we discussed a long time ago, maybe in incompressible flow, etc. When we discussed about non-dimensional parameters like Mach number, Reynolds number, etc. Please look at this. This is flow past a cylinder. So what you see on the left-hand side is the flow visualization. You have maybe water flowing across a cylinder. So what you see there as a circle is the end view of the cylinder. A quite familiar picture you would have come across that in fluid mechanics. So you have the cylinder here, and you have the flow fairly turbulent and forming the wake. As we know, the flow separates and then curves around, leading to the formation of a sort of unsteady dissipative region, which is what we call as the wake. And we know that this whole phenomena is dependent on the flow Reynolds number. That is the free stream flow Reynolds number, R equals rho Vd by mu. And one way, or rather the most useful way the flow phenomena is represented in engineering applications is as a function, as a plot of CD versus Reynolds number. Y-axis you have, x-axis you have Reynolds number, y-axis you have CD. And we have a curve, a famous curve. It has a linearly dropping region and then slightly flattening, and when towards end flattens off and there is a sudden dip, and then it recovers, etc. What is this dip called? This is CD Reynolds number curve. Well, what is that region called? Can you recall from fluid mechanics or wherever you have seen it before? Somebody, please. Can anybody recall that? What is called that? What is the name for that particular region where you see a sudden drop in CD value, drag value? You have not heard that? Have you heard this word drag crisis? It's usually known as, I don't know whether you have come across it. Usually it may refer to it in fluid mechanics, but not necessarily. This is called drag crisis, actually. That is that sudden drop there. Anyway, that is not important for us for the present discussion. The only reason that I quoted this image is to impress upon the importance of non-dimensionalization. Why is it so? Because you have two parameters there, CD and Reynolds number. CD is non-dimensionalized, Reynolds number is non-dimensionalized. So all that I need to represent flow past a cylinder is to have this curve. So if I have this curve, if I have this experimental curve, and then I can take for a given value of Reynolds number, what is going to be the CD, I can read from this. And once I read it, I can use it for any combination of my interest. Now, this, what you see here, the plot may be created for air, most probably, yes, it is. Air or water, actually, maybe. Based on experimental measurements, they've made a plot of CD versus Reynolds number. Now, I want to use it for, say, maybe a chemical engineering person wants to use it for, say, flow of methane past a small cylinder, a pipe or something, across a pipe, not through a pipe. So, and the person wants to know what is going to be the wake structure. So he or she can use this graph definitely without worrying about whether the graph is originally created, the experiment is originally created with water or air, or what was actual dimension of the cylinder which was used in this, etc. Because the data is presented in terms of non-dimensional parameters. So I can use it for a different cylinder. I can use it for a different fuel gas. I can use it for a different density. I can use it for a different velocity, whatever. Though all the parameters are dependent on these variables, since the data is presented non-dimensional form, I can use it for anything as long as I keep checking for the Reynolds number and CD value of my interest. So suppose that I'm working with R equals 2000, or say R equals 10,000. All that I need to do is to read RE from this or read the value of CD from this graph corresponding to R equals 10,000. So as simple as that. So uh, I hope you are able to appreciate the advantage of it, because there are several driving parameters otherwise. Rho V D by mu. Say, right, Reynolds number is dependent on rho, depends on velocity, depends on the diameter, depends on the viscosity, etc. But despite all that, I am just using a single curve. I'm not going for different curves for a given rho, vary the other things, other parameters, etc., etc. Similarly, CD is dependent on the drag force and the whatever the numerator, rho v squared a, etc. So there also you have density, velocity, the area, etc. But then, since it is expressed in terms of non-dimensional parameters, we can make use of this data for experimental analysis. That is for across, it can be applied across a set of variables which are not necessarily represented in the experiment. Okay, so probably it is very obvious to you, but I am trying to repeat it so that the key topic that we are talking about is non-dimensionalization. So I want you to be aware of why non-dimensionalization is important. That's why I just took this famous graph to drive the concept home. Anyway, so we get back to our business. What we are going to do is we have this governing equations, and we are now trying to express them in terms of non-dimensionalized form. So we are going to non-dimensionalize the governing equations. And that is not very complex as long as we have some meaningful representation for the parameters, the variables. The non-dimensionalization is quite straightforward. So velocity, the most natural way to have a non-dimensional form for velocity is to have the local velocity divided by the free stream velocity. So V by V infinity. Similarly, density, rho by rho infinity. What is rho? The local density, density, and rho infinity is the free stream value of density. Similarly, temperature, the static temperature, the local static temperature divided by, now temperature and density, viscosity have, pressure have slightly different ways of non-dimensionalization. That is because of the way that they can be connected to other parameters, other non-dimensional parameters. So P by rho V squared, rho V squared has the same unit as pressure, we know. So rho infinity V infinity squared, that is what used for non-dimensionalizing P. Similarly, temperature is non-dimensionalized by V infinity squared by Cp. Say, please look at the relation between the two. V infinity squared, which is something related to kinetic energy, right? And energy, that is which will have the unit of Cp into T, right? So we have T on the top. So the numerator is V infinity squared by Cp, will have the same unit as temperature. So that's non-dimensionalizes the temperature. So now what we are going to do is to rewrite this equation using these non-dimensionalized forms, which may be laborious, but it's quite straightforward conceptually. All that I have here is, I'll try to point out one or two parameters. Say rho, the partial I'll just take the first term, partial d by dx of what I need there as per the equation. What I need there is rho u. I'm sorry. Dou rho u by dou x. Dou rho u by dou x. I'm trying to non-dimensionalize rho u and x. So when I do that, based on the approach that we just mentioned, the term will transform to dou of rho by rho infinity u by v infinity. Instead of rho, I am writing rho by rho infinity. Instead of u, I am writing u by v infinity. Similarly, the denominator dou x, I am non-dimensionalizing x by L. L is the transverse, sorry, the streamwise length or the dimension of the body. So x by L is the non-dimensionalized form for x. So all that I have inside the bracket is dou partial d rho by rho infinity u by v infinity by partial of x by L. So dou by dou x of whatever you have. So this is nothing but replacing the original differential terms using the non-dimensionalized form for the respective variables rho, u, and x. Now this will have some terms which will be common to all the three, which are what we have taken outside and multiplied by rho infinity v infinity by L, because otherwise we have the say if you look at the numerators, each of them is divided by rho infinity v infinity, right? So divided by rho infinity v infinity. So I need to have outside the bracket, I need to have a multiplication by that. Similarly, each of the denominator terms are divided by L. So that is dou by, so it's in the denominator. So division in the denominator. So to offset that, I need to have a division in the numerator for the term that is outside the bracket. So rho infinity v infinity by L is a common factor to all of them. So this way we can non-dimensionalize the energy equation. Sorry, the continuity equation, okay, which can be further simplified as rho by this one, etc. Because what is rho by rho infinity? That say I'm just highlighting the notation that we are using. Each non-dimensionalized parameter is used by a hash or a dash on the top. So x hat or x dash or whatever you call it, x bar actually, x bar. So x bar is the non-dimensionalized form of x. That is, x bar is x by L. Similarly, rho bar is equal to rho by rho infinity. Okay, so using that notation, now I just transform this equation as dou by dou of x bar, rho bar, u bar, etc., etc. So this is a non-dimensionalized form of the energy, the conservation equation for mass continuity equation. And similarly, no, I'm not going to repeat the whole thing. The momentum equation in the x direction. So by the same approach, that is u being replaced by u by u infinity, rho replaced by rho by rho infinity, p replaced by p by half rho v squared, rho infinity v infinity squared, as we have seen. And similarly for the energy equation also. Now, so all that we have done now is to non-dimensionalize the governing equation. Any questions so far? Okay, then I just tell you what we are doing, and I'll briefly say where we stand now. We have the governing equations that can be applied to hypersonic flows under the assumption of steady inviscid assumptions in inviscid conditions, and we are trying to non-dimensionalize the solution, or non-dimensionalize the equation. We have defined appropriate terms for each variable so that it can be expressed as a non-dimensionalized form. And third, we applied that, we rewrote the equations using the non-dimensionalized forms. So now we have got a series of equations which are in the non-dimensionalized form. Or in other words, we have now the non-dimensional form of conservation of mass, momentum, and energy as applicable to steady inviscid flows. Okay. Now, if we have to solve this, actually we are not going to solve it, but we are going to look at the nature of the solution without solving them. That's what we are going to do. But then if you need to know about the solution, you need to know about the boundary conditions also, right? These are governing equations, partial differential equations. They can be solved. If you have to solve it, you need to have a set of boundary conditions, which we are now studying in CFD, right? You need to have, if you have to solve the equations, you should have a set of conservation equations, which should be solved subject to a set of specified boundary conditions. Now, what are going to be the boundary conditions for this? For that, we need to understand what are the boundaries. Just look at the picture. You have a bow shock, which is formed in front of a blunt body. So, okay. So if you are considering this as the flow field, and if I have to study the flow field, I'll just try to mark it here, and I want you to speak up. For now, I'm just, for the sake of this discussion, I'm just considering a domain which is combined by this, which is bound between these two red regions. Okay, and I'm interested in solving the flow field in between, particularly with the interest of calculating what is going to be the pressure distribution on the body. That is, what is going to be the pressure distribution on this. Okay, my question to you is, what are the main boundaries of the domain? Where am I solving? Or if I were to solve this, what are I'm not asking for the boundary conditions, but which are the boundaries that I should consider? So please give your.
Sure. Two subsonic boundaries in top and bottom. At the center, there's a supersonic.
Sorry. So sorry, you are talking about these two now, the one that I have ticked now.
Yes, sir. Top and bottom, they're subsonic layers.
That's okay. Then
at the center, we have a supersonic layer.
Sorry, say that once again. What did you say?
Supersonic layer.
Supersonic layer there. No. See, I'm asking about the boundary. I'm not asking you about the domain. Domain, yes. The region between the this one. But what are the boundaries that we are playing around with? Boundaries, the extrema of the domain. What is the upstream boundary? That's first question. Upstream, the front, the first boundary of the domain.
The shock itself, sir.
Yeah, exactly. So the oblique, the shock, which is a detached shock, is one boundary. I mark it as B1. So the shock is one boundary. That's correct. Now, which is the other boundary?
The object.
The object, the surface. So surface of the body. So these are the boundaries in which actually let's forget about the lateral directions. Anyway, I mean, wherever it extends, I can apply it accordingly. But primarily, the flow boundaries are the shock and the body itself. So when I say applying boundary conditions, I am concerned about values at the shock. At the shock means just after the shock, and at the surface, which means just at the surface. So when I say boundary conditions, I'm talking about values in the near shock region, or rather just downstream of the shock, exactly downstream of the shock and exactly on the body. These are the boundary conditions. Okay. So if we are able to appreciate these are the boundary conditions, then we can think of what are the boundary conditions going to be. So let's first talk about the surface. Now, what do I mean by boundary conditions? Boundary conditions means values of the variables at the boundaries. What are the variables? Variables like pressure, density, velocity, etc. Whatever I'm solving for, they are the variables. So velocity is a variable. density is a etc. Pressure is a variable, etc. Right. So now we are trying to understand what is going to be the nature of the boundary conditions. So, for example, at the surface, velocity is going to be, we are considering inviscid flow, which means that the flow is going to be parallel to the surface. That is, there is no normal component to the flow to the surface. Why? Because there is no viscosity. It's just slipping past the surface, right? So it's basically tangential inviscid flow. So which means that the normal component is zero. So in other words, the surface is defined by the condition that the normal component of velocity is zero, right? So I can write it as v bar dot n, that is the unit vector n is equal to zero, right? It's a vector quantity. So we have v bar dot n equal to zero, right? Now, by using vector notations, it can be written in terms of the three components of v, that is x, y, and z. I mean, the components along x and y, x, y, and z. So x component being u, y component being v, and z component being w. We can write it as u nx plus v and y, etc., as shown here. Okay. So now we can write the boundary condition. So this is equal to zero at the surface. So the net velocity at the surface is zero, right? Which means that in the using now, I'm not interested in u. I'm interested in u bar because I want the whole thing non-dimensional flow. So u, or rather, u bar is u by v infinity, right? Similarly, v is v bar is v by v infinity, the mainstream flow, which is aligned along the central line, etc., of the domain. So which means that I can replace all these by u by v infinity, etc., and v infinity is common and it's a constant, etc., which means that I can rewrite the equation as u bar nx plus v bar ny plus w bar nz equals to 0. This is a non-dimensional boundary condition, or boundary condition in the non-dimensional flow. Okay, for velocity on the surface. Okay, so this gives us a set of boundary conditions which I can apply on one of the boundaries, which is the body itself. Okay, now how about the other? As you just mentioned, the other boundary is nothing but the shock itself. And for the shock, let's assume we are just considering the normal shock region. When we are considering the normal shock region, we know what is P2 by P infinity, right? All that comes from our familiar normal shock equations. P2 by P infinity, rho 2 by rho infinity, U2 by V infinity. All these are part of the non-normal shock relations, and where we get all these ratios in terms of the free stream velocity. Okay, so similarly P2 by P infinity, we can, so P2, since we have a slightly different form, non-dimensionalization for P2, we can still derive that in terms of P2 by P infinity as gamma P dash M infinity square based on this relation. So it can be also written in terms of P bar. P bar is the non-dimensionalized form for pressure with the division of rho V infinity squared, etc. Okay, so now look at these relations. These directly lead to their values for their non-dimensionalized form. So P bar 2 can be written as 1 by gamma infinity squared plus etc. All that comes from what I have written here. P2 by P infinity is equal to gamma P bar M infinity squared, from which I can write P2 bar as a function of P2 by P1 and gamma M infinity squared. So the whole thing gets divided by gamma infinity squared. P2 by P1 I have already there on the left hand side. So if I combine the two, I can write as P2 dash is equal to, or P2 bar is equal to 1 by gamma infinity squared plus 2 by gamma plus 1, etc., etc. So nothing new here. I have just used the normal shock relations. I have just used the non-dimensionalization that we discussed and combined the two in such a way that again I have the shock conditions in terms of non-dimensionalized parameters, non-dimensionalized variables. Okay, so P2 bar, ρ2 bar, U2 bar, V2 bar, etc. So all these belong to the shock conditions or the conditions just after the shock, and they are expressed in terms of non-dimensional parameters. Okay, so once we have that, we have now a situation where we have the upstream conditions, upstream conditions, which are these. We have the downstream conditions, which is the condition on the wall of the body or the surface actually. Now let's have a closer look at these conditions, the boundary conditions at the ball shock for hypersonic flow. Now, whatever we discussed so far is applicable to any domain of supersonic flows. Wherever you have a shock, all this is applicable. But since our interest is in hypersonic flows, we are now looking at the form of these boundary conditions when the flow is hypersonic. So, for example, P2, and say what you have here in the box here is what I just copied from the previous slide. Okay. So these are the non-dimensionalized forms of P2, ρ2, U2, and V2. Okay, U2 is the x component of velocity, V2 is the y component of velocity just downstream of the shock. Now, they can, for hypersonic flow, that is as m1 tends to infinity, that is for high values of hypersonic flow, or rather, when the values of Mach number tends to infinity, I can further simplify these relations. P2 can be written as 2 sine squared beta by gamma plus 1. I want you to check that. It's quite straightforward. We have done that for oblique shocks, etc. multiple times. It's quite straightforward from here. 1 by gamma infinity squared. That will be negligible because m infinity is very high. So this term vanishes. And in the remaining term, sine squared beta will tend to become beta squared because beta will be, in fact, no, we are not using that here. Even for larger betas. So 2 sine squared beta and 1 minus 1 by m infinity squared also becomes 0 because m infinity is very high, etc. So all that remains is 2 sine squared beta by gamma plus 1. And ρ2, again, this we have done earlier, gamma plus 1 by gamma minus 1. So you have gamma plus 1, m infinity squared, sine squared beta, these two becomes negligible. So the rest gets cancelled in the numerator and denominator, and what remains is gamma plus 1 by gamma minus 1. Similarly, for U2 and V2, they can also be simplified by the same approach. Please note that the 1 here will not vanish because in comparison, what you have is once you extend the limits to the second term to this term, that boils down to 2 sine squared beta by gamma plus 1. Now, since 2 sine squared beta by gamma plus 1, we cannot say that's a high value. Actually, that will be low. So that cannot be neglected in terms of 1. So that's the reason this 1 has to be retained. Okay. So 1 minus 2 sine squared beta by gamma plus 1 is U2. And similarly, for V2, we get an expression like sine 2 beta by gamma plus 1. Okay. So we have now the non-dimensionalized forms of boundary conditions. I just want you to look at these conditions, P2 bar, ρ2 bar, U2 bar, and V2 bar, and see whether they depend on the free stream Mach number. The non-dimensionalized forms of boundary conditions, do they depend on the free stream Mach number? Do you see free stream Mach? No, because none of the expressions have free stream Mach number. Actually, the white box here has free stream Mach number everywhere, m infinity squared, etc. So for supersonic flow, they are dependent on Mach number, free stream Mach number, non-dimensionalized boundary conditions. But when we extend to hypersonic limit, as the Mach number increases, they become less and less dependent on infinite Mach number, the free stream Mach number, and eventually we can say that for high Mach number flows, high hypersonic flows, they are practically independent of Mach number. So the boundary conditions after the shock are independent of Mach number. Okay, that's what we conclude from here. How about the previous boundary conditions? The on the surface, that also I have written u bar nx plus v bar ny plus w bar nz equal to 0. Here also we don't see any Mach number. That is u bar is u by v infinity, etc. So we are there also there is no the non-dimensionalized forms are not dependent on the Mach number implicitly. So on both sides, the boundary conditions are independent of Mach numbers. Okay. Now let's consolidate the observations that we have. Time is, oh, I'm sorry. I think I took a long time to. I think I'll stop here right away. Anyway, I have to revise this once again before I conclude. I stop here. I have one more. This one I want to give an assignment, fairly straightforward one, but I just want to explain that. So I'll stop here. Just get. I didn't notice the time at all today. So I said I stopped earlier. Assignment 2. Quite straightforward. This is just an application of Newton's law. I want you to do it yourself and get a feel for what we have discussed as part of the theory. So for that is what Newton's law as well as the modified Newton's method as well as Lee's modification for that method. Details are written here. You have a body which is shown on in the picture. I want you to calculate the CP distribution as a function of the theta for a range of theta from 90 to 10 degrees. What do we mean by the variation of theta? That is, if I were to actually plot this static pressure here on the body, I can probably consider this as the body points as a function of theta. Say theta will be, say if I consider like this, I can have along the axis and then rather say if the vertical, this one will be with the axis, it will be making 90 degrees, etc. So I can consider it like this, right? So for different values of theta. So I just want you to consider a range of maybe on the lowest you take as 10 degrees and highest 90 degrees, or 9 to 10 degrees, or the other way around. And so theta, you use theta to vary this way. And it's a plot what I am looking for. So on y-axis you can, x-axis you can have theta, y-axis you can have CP. You can take appropriate this one for theta, but the range should be covered. And then you should plot the CP variation based on Newton's method as well as the modified Newton method, etc., Lee's method, etc. And then you should compare. And very importantly, you should note down your important observations, how that varies for different Mach. And this has to be done for different Mach numbers. Actually, each group has to do it for 2 Mach numbers. I've written that in the this one here. Group 1 has to do for 520. That is Mach 1. M infinity is 5. M infinity equals 20. Group 2 for M infinity equals 6. M infinity equals 24. So I have given a lower Mach number and a higher Mach number for each group. So you should plot them on the same graph, compare, and say what do you infer from that with respect to the applicability of Newton's method as well as the Lee's modification, the impact of it, and the impact of Mach number on such simplistic models. Okay. So this is what I want to be submitted. You can submit it by 24th next week. It doesn't take much time anyway. And one more, this one, each team should upload the assignment by 24th. And I will, when we discuss them, I want everybody to have the copies of the presentation within the team, so that I can ask anybody to give the presentation. So it will be my choice whom I call. It will be fairly arbitrarily. I'll call a group member to present it. So the person that I called should present it. This is obviously to make sure that everybody is familiar with the calculation and everybody is familiar with what is presented in the slide. Okay. Thank you. I stop here. Any quick question that I need to address? Otherwise, we'll meet in the next class.